my pleasure to introduce two of my colleagues, Craig Labovitz and Abha Ahuja, and their slides, as I said, will be live momentarily.
Thank you, Susan.
You're welcome.
Okay. Thank you, Susan. To begin, I don't have any food recommendations for you, nor in this talk are we going to talk about sniffing anyone's network, nothing that controversial. Instead, we'll talk about injecting faults into people's networks. So, a lot less controversial. So I'll wait just a second as people come in, but we'll be talking, this is a follow-on talk to our last NANOG talk where we said really bad things about BGP. Today we'll just say really bad things about policy, not so much about BGP. This work is in collaboration with Abha as well as some other folks at Microsoft Research. So in the last NANOG, we showed a couple of, went through a talk that really explained, at least in theory, BGP has some really awful convergence properties. That is, in theory, you can actually create a complete graph of BGP speakers without any policy that, unlike RIP or unlike other protocols, the AS path leads to some really horrible characteristics, or at least from a theoretical point of view, you can look at during convergence. And by convergence, I really mean after a fault, after a multi-home site loses one of their connections, how long does it take for the majority of other internet routers to begin recognizing the backup or alternative BGP path? So it turns out, at least from a theoretical point of view, the answer is pretty bad. It's n factorial, where n is the number of BGP speakers. It's actually a number that's far worse than RIP or other protocols. And we also presented quite a bit of measured data looking at faults we had injected over the course of 2 years, where we looked at numbers ranging from 10 to 30 minutes at the upper bound for a given BGP change to propagate throughout the internet. So really big numbers. From a theoretical point of view, n factorial states, and from the measured times up to half an hour. But as it turns out in practice, the internet isn't a complete graph, that providers have the nasty habit of actually having policies and filtering customers. So in practice, we really don't see the millions of updates we would have predicted, and that's really because the internet isn't a nice complete graph and there's policies and other things in there. So the question we're looking at in this talk is, okay, what are really, given a provider's network, given notions of policy, what really is leading to these half-an-hour convergence times? What is it about internet policy and internet topology? And what role do these play in convergence times after failure? That is, the time it takes for BGP messages to propagate. And we have a number of questions. Given a physical topology, can we estimate time for convergence? Do convergence properties of different ISPs differ? Are state topologies different? And is there anything we can do to improve BGP convergence? So rather than hold everyone in suspense, I'll give you the answers right now. They're yes, 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 and maybe. So we repeated some of the very similar experiments we talked about at the last NANOG, but this time instead of just looking at how a single fault propagated, we decided to simultaneously take different prefixes and failover, inject BGP withdrawals and announcements at the same time into different providers, and watch how these different prefixes from the different providers filtered through the network. So we did this with some 30 different providers, and we also had a number of surveys, work Abha did, to try to understand, when we saw the results, understand, where did this path come from? Why is this really transit, backup transit, customer, something of someone else? Trying to understand what led to some of the paths we observed. In the next couple of slides, we won't focus on the great mass of data we collected. Instead, we'll really focus on just sort of a case study of 3 providers. We decided to pick, really to illustrate some of the intuition behind this. We'll talk about 3 providers, all at May West. These 3 providers are all direct peers of another provider who is mainly located in Japan. So in steady state, all direct peers, all the route always had an AS path of length 2, all very similar. When we did pings or trace routes, also the results were all very similar. So this is just, again, a graphical view of what I said. We had 3 providers all at May West, took 3 different prefixes. We sent BGP announcements and withdrawals for these 3 different prefixes into the 3 different providers, and essentially watched what happened from the same Japanese provider. In steady state, again, they're all directly connected. So steady state look exactly alike. But when we actually looked at the data measuring the convergence latencies, that is, from the time it took when we injected a fault into ISP 1, 2, and 3, how long did it take for the Japanese ISP to reach convergence, we saw very different data. In fact, it's much more pronounced when you look at slightly newer graphs we have over longer data frames. But it turns out ISP 1 and ISP 2 were close, but ISP 3 took much longer to converge. So initially, ISP 1 and ISP 4 had direct peers. When we actually injected the fault, about 96% of the time, we'd see the backup path. And I'll have my little pointer here. We'd see the AS5, AS4 backup path, followed by a withdrawal at an average of 92 seconds. And it turns out only 4% of the time would we see a withdrawal without ever seeing the backup path. And this is because, in some cases, the withdrawals traveled faster along P2, reaching ISP4, than the withdrawal along the steady-state path. So if the backup path is ever withdrawn before the steady-state path, we'll never see an intervening announcement. Instead, the backup path will be deleted. Since it is not the active route, we won't see the withdrawal until the withdrawal finally reaches ISP4. Make sense? I don't see anyone nodding. Yeah. Okay. Okay. Next example is between the mid-level ISP. Again, this is the content, the hosting ISP. Again, this is data MA West, same provider in Japan, watching the differences in the path. In steady state, they had a direct peering. But they also had a number of different paths. 63% of the time, we'd see the red path announced. But 7% of the time, we'd see both the red and the blue announced. And only 7% of the time would we see a direct withdrawal. And again, for the withdrawal to happen without the intervening blue path or red path announced, it must mean that the withdrawals traveled faster along both P3 and P2 than they did along the steady-state path. And a lot of the speed of the withdrawals is there's a uniform or distribution of the min-route adver timers. So the min-route adver timers are not on a per prefix basis on most major router implementations, but they're really on a per peer basis. So the timer delay that ISP5 would add for any route traveling along that path is really based on any earlier instability that it sent between 5 and 6. And 23% of the time we saw a large number of different other paths, including the thing in green. When we did the study, we noticed really a huge number of paths that made no sense. We had, tier ones being customers of small content providers, who were then customers of others, routes taking very strange courses. On one example, we had two routers in May West who had a direct route between them. When we failed that path, the route actually ended up going through several small Mediterranean countries before it finally was withdrawn. And all of these just really point to the difficulty in getting these filters right. Huge number of cases where just the filters were wrong. And when we finally asked the different ISPs involved, why are you transiting, Italy? The answer was, of course, always, we aren't. And when we showed them the data, they said, oh, we shouldn't be. So this is a final example that, I'm sorry? No, I don't work for him. I work for Microsoft, which is close. What? I don't understand the question. Maybe we'll, okay. So this is the last example. One of the things hopefully you'll notice as I go through this example is that as we move from a tier 1 to the tier 3, the topologies are getting more complex. Not the steady state topology. In steady state, they're all direct peers. But what's changing is the backup topology, the alternative paths we see as we go through the three different providers. And this one gets quite a bit more complex. We actually saw close to some 70 or 80 different paths which fell into the 27% other. Quite a bit of variety as the failover happens. And again, this is just recording that about 36% of the time we just see a primary backup path announced. And again, by the way, when we inject these withdrawals, it's our prefix. There really is no other route there. These are the routes that we're seeing with a single homed prefix being withdrawn from ISP3. So in the course of withdrawing that prefix, 36% of the time we'd see the red backup path, followed by withdrawal. 35% we'd see this, red and blue, and so on. So I'll now hand the talk over to Abha, and she'll actually talk about why are we seeing these different topologies from these three different providers. And all you, Abha. This is a laser pointer. Don't point it at them.
I can't. Okay, so the first thing that we're going to talk about is why are there all these different levels of complexity? In the three different examples that Craig showed, you could see that the topologies got very complex and the number of backup paths was increasing. To set the stage for that, we're going to present a provider relationship taxonomy. People are often talking about the different relationships between providers, but we want to set the stage by providing some concrete definitions so there's no confusion. The first one we're going to talk about is transit relationships. So this is basically your customer-provider relationship. The customer sends the customer routes to the upstream provider. The upstream provider is going to send default-free or just send default to the customer. In a peer relationship, we're talking about a bilateral exchange of customer routes. So basically, when two people peer, they're only going to send their customer information and their network information rather than a full routing table. And backup transit, while may not be all that common, is one of the things that we found from talking to providers and looking at some of the interesting data, so that kind of explains some strange things that we saw in the AF path information. And so what I'm defining that is that actually a peer relationship becoming a transit relationship based on failure. So basically, two peers have an agreement with each other that when one of their upstreams fails, that they will actually turn to the peer for default-free route information. So basically, these relationships constrain topology. Based on the relationships between providers, whether or not they're customer-provider or peer relationships, is going to determine the number of possible backup paths. So when we talked at the last NANOG and we said that there's n factorial amount of states that you need to explore in order for your system to converge, the constraint is actually based on policy. So depending on how your policies are set up, you're going to see some subset of that n factorial. So I'm going to show an example from the real world, basically. So these are, this diagram shows a relationship between 5 ASs that was actually in our data. And so here you can see that customer 2 is, AS2 is actually a customer of AS4 and AS5, but has a peering relationship with AS3. And so from here, you can see the possible paths that node 3 is going to actually see. So node 3 can possibly get to some prefix x with the path of 21x, with the path of 421x, and in the case that 4 actually fails over to its alternate path, you might see 4521x. Now it's very interesting to note here that customer 2 is, or AS2 is actually a customer of AS4 and AS5, but AS5 is actually a customer of AS4 itself. In this diagram, you can see that AS2 is a customer of AS4 and is a customer of AS5. But it's also buying, but AS5 is also a customer of 4. So you can see that this path is, AS2 is buying a service from AS5 and AS4, even though 5 actually is a customer of AS4. Is that clear? Well, one of the things that you notice is that if you actually stick to a hierarchical relationship between providers, you can eliminate some of the possible paths that you're going to explore. So from here, I took out the relationship between AS2 and AS4, they're no longer customers, and kept this to be a hierarchy. So AS2 is buying service from AS5, who then buys service from AS4. So you can pretend that AS4 might be a tier 1 or something. And so you note that the possible paths now are reduced. We've eliminated one of the possible states that each one of these ASs is going to explore. And so therefore you would think that based on the fact that you're eliminating the number of states to explore, that your convergence time is actually going to be much faster. So strictly hierarchical relationships eliminate exploring some extra states because policy controls the number of possible paths you're going to explore. But it turns out that the number of paths really doesn't matter. It's really a function of the longest AS path in the system. So if you notice from my past diagrams that the longest path in this system, which is following hierarchical relationships, is actually 3, 4, 5, 2, 1, which is the same in this. So this diagram actually shows that convergence is related to the length of the longest possible backup AS path between two nodes. So here we've plotted the longest observed AS path between an AS pair and the average convergence time. So you can see as the longest observed AS path increases in length, that the convergence time actually increases as well. So what does all of this mean for convergence time? Convergence time is related to the length of the longest AS path that needs to be explored. So before failover occurs, you actually need to withdraw all the alternative paths that you have. This means that the final withdraw message for a given withdraw must propagate across all of the ASs in the longest AS path, and that's where all of the delay comes from. And so you can see this applied to Craig's slides, which actually showed that the longer the backup path, the longer it was going to take to converge. And this longest path is related to the policy relationships that you have between providers. So providers with shorter AS paths typically exhibit faster convergence. So what can we do about this? Well, there's a couple of different possible solutions to this BGP convergence problem. One is an entirely new protocol. We can just throw it all away and start over from scratch. One of the other possibilities is turning off the min route advertisement timer, because that limits how fast updates are actually propagated. But doing this itself has some trade-offs. Another possibility is no transit, just peer with everyone and have a full mesh, but we can all see the obvious problems with that one. Another possibility that we've been working on is the possibility of tagging BGP updates. So you can provide a hint so nodes can detect bogus state information, so you no longer have to explore all those invalid paths. And so if you guys are actually interested in the details where we prove all of this, you can check out all our papers that are on the IPMA website. And if any of you are interested in participating in our study by providing us with more policy information or possible peering sessions, just please send us an email. Question?
Avi Friedman from Akamai. When you say it's related to the length of the AS path, that's the number of distinct transit or re-advertisement ASs in the middle, not the length of the AS path. So if there's padding or other things.
You're talking about prepending? Right.
Yeah. Okay, so prepending doesn't have an effect. Okay.
So when you say peering with everyone is one way of fixing it, obviously everything is one hop path, blah, blah, blah.
I'm sorry, I can't hear you.
Sorry. If peering with everyone, having a one hop full mesh for everything solves the problem, the question is there a threshold below which more peering is making the problem worse that you're able to observe versus any direct horizontal connections within the hierarchy making things better?
Well, the thing is that it's actually related to the longest possible path. So when you peer with everyone, that path is small. But at the same time, when you also have, when you're peering with everyone, you're gonna more quickly explore those states.
Well,
you see what I'm saying?
Okay, so let me refine the question then. Is it related to the longest selected path out there, or is it related to the longest possible path?
The longest possible path based on your policy. So if there is such a path, like if your normal path is like 2 AS hops, but you have a backup path that's 7 AS hops, it's a 7 that actually constrains it, even though you've currently selected the one that's 2.
Well, the fuller
you will fail over to that.
The fuller your mesh, the longer the potential backup paths are, right? But the shorter the actual selected paths.
Yeah, let me step back a second. By the way, it's not just the longest path you have in your RIP at any time. It also is highly dependent on other people's policies. It's really the longest possible AS path possible for the system. I don't think did you understand? No. We agree. We didn't understand your other question. But no, you can ask it.
Okay. The fuller your peering mesh, right, the more possible ways there are to get between 2 points, right? They are possible, but they won't be selected because you'll also have more shorter paths, right?
I think that what we're saying, I think that one of the things that we're saying when we're suggesting, hypothetically, that you could peer with everyone and that would reduce the length of the longest AS path, we're actually meaning peer with everyone so everything becomes one hop away.
Right. So.
Which is actually different than, to some level is related to increasing your peering mesh, but you're right. If you do peer with a subset of folks, you actually increase that possibility.
Okay. All right.
Does that make sense?
I need to think about it more.
You talked, sorry, Alex Bly from EXO, you talked about the longest possible path being the deciding factor, and in the diagram you had that thing that you call the vagabond path, which we presume was unintentional. I guess my question is, what percentage of the, what percentage would one tend to reduce convergence times by if these unintentional paths, which either appear because of misimplemented policy or I've seen ones appear because of router bugs, were removed, and you only ended up with long paths due to people having...
So you're saying what percentage convergence improvement would you see if you eliminated all the misconfigurations?
Yeah. Yes.
Yeah, when we looked at the vagabond paths, those were really pathological outliers, and we ended up filtering those from a lot of the other analysis. When a vagabond path occurs, in general it can be bad, in fact really bad, transiting maybe up to 30 different ASs before you come back. But we managed to filter those out by looking at paths we saw at the beginning of the study, the end of the study, as well as normally many of these paths originate due to one or two ISPs filters being bad, and which suddenly allow a large number of these paths to occur.
But that could contribute to some poorly configured third parties router could contribute to two other people suffering some form of convergence delay of perhaps several minutes, is what you're saying.
Yeah, yes, that when these pathological outliers occur, they can be really bad, and they not only affect the person who broke the filters, they affect large sections of the rest of the internet. Good filters are important.
And for the next discussion?
And it leads right into the next discussion, yeah. Randy.
Randy Bush-Ferrier, you've lent a new meaning to pathology. The statement that the convergence problems are proportional to the longest configured paths seems to conflict with your statement that the solution for me is to peer with everybody, because that does not say that there are not complex relationships behind everybody.
Right, the theory is to treat everyone as a customer.
I think we proposed it in jest because we were basically implying that you would peer with everybody so that you would account for all those complex
Everybody has to peer with everybody and have no more complex relationships.
Right, and that's
for your
why
statement to
it was
hold.
Basically in jest.
Which means that everybody, probably due to my having read your other paper, would also be helped if everybody were completely global and met at all the same points. Which I think is an interesting challenge.
Yeah, we never said it was a good solution.
It was
Chris Williams, Third Rail. When you're saying the longest available path has an effect on your convergence time when there's a failure, and that's a bad thing, I can certainly see how if you're single-homed, when you withdraw your advertisement, that affects how long it takes for your withdrawal to get out. Back in the real world, if you're single-homed and you're withdrawing your advertisement, you don't care how long it takes because you're not getting any traffic anyway. In a real case where you had multiple paths, if one of them goes down and you withdraw that, the actual convergence time would depend on the longest path being withdrawn that was shorter than the next available path, wouldn't it?
Yes, in fact, we spent a lot of time at the previous NANOG talk showing that when we did do experiments failing over between two paths, and it was a sufficiently long prepended backup AS path, it was exactly equivalent to withdrawing a single-homed path. But you are right, there you start to get into a middle ground. You have to actually get to length when you're doing failover to getting past the threshold of longer than the, I can't say this anymore, longer than the shortest, yeah. You have to be longer than the shortest primary path. Yeah, I agree with you, yeah.